Suppose that f is a function from D to the real number line, and let C be an accumulation point of the domain D. If the limit as x approaches C of f of x equals infinity, then for every sequence Sn in D that converges to C, with Sn not being C for all n, we have that the limit as x goes towards infinity of f of Sn equals infinity. I tried to color code the antecedent of this conditional plus the antecedent and the consequent of this conditional. This might help us to be able to see the proof and to understand if you need to pause to see where any of the other details are. So to begin, let's suppose that, now this is going to be in blue, we're going to suppose the antecedent, we're going to suppose that the limit as x approaches C of f of x is equal to infinity. Okay, and then we're hopefully going to use that in order to be able to show the consequent, which itself is a conditional. So in that conditional, it's actually it's not really conditional, so it's a universally quantified statement here, for every. So when we go into the second part, we're going to have to let an arbitrary one of these objects in green be given. So let Sn be a sequence in D with Sn not equal to C for all n, and suppose that Sn goes towards C. So this is a sequence in D that converges to C with none of the objects or none of the terms of the sequence being actually equal to C itself. Okay, then in red, what do we need to show? So I'm not affirming my consequent here. Instead, I'm just noting, what do I have to show? I have to show the consequent. I have to show that the limit as x approaches infinity of f of Sn is equal to infinity. Okay, so to that end, let's begin our proof. So we want to prove something's converging to infinity, so standard beginning, let m be given. And we're going to hopefully show that f of Sn is always larger than m. Okay, now in blue, because this follows from the limit as x approaches C of f of x equaling infinity, we can say that since the limit as x approaches C of f of x is equal to infinity, we have that there is a delta greater than 0 such that f of x can be made bigger than m whenever x minus c happens to be less than delta, because that's the definition of x approaches c of f of x equaling infinity. Okay? Furthermore, since we have the antecedent here of a sequence that's heading towards C, Sn heads towards C, that means that we can say that since Sn converges towards C, we can choose a capital N such that we'll know that S sub n minus C is less than delta for n bigger than or equal to capital N. Okay, so then what is the ending part? Well, now then for this same n we have that f of Sn is bigger than m for n bigger than or equal to n. Because if we look carefully back here, what we have that S of Sn minus C is less than delta, and whenever x minus c is less than delta, we know that f of x is bigger than m. So S of n minus c is less than delta satisfies x minus c less than delta for x being Sn, and that means that f of Sn is bigger than m. But what does that mean? Well, that would mean, thus, we'll put this in red because it's the conclusion of what we wanted, we get that the limit as x approaches infinity of f of s sub n equals infinity as desired. And that is the completion of the proof.